Hello, my name is Victoria Ebert, and my project is deep audio transcription, or using a neural network to transcribe an audio file into a MIDI file. First, I just want to break some things down. Transcription is the act of converting something to a symbolic format. The specific symbolic format, often used for musical transcription, is MIDI. MIDI stands for Musical Instrument Digital Interface, and MIDI files record the precise starting and stopping of notes, as well as which note is being played and the velocity with which it is played. The goal of this project, in the long term, is to be able to produce a symbolic format of any audio file that could then be converted into playable sheet music. This includes orchestral pieces with multiple instruments, or even non-musical, nonsensical audio, such as a train horn or a cow moo. The broader category of what my project is music information retrieval, or MIR. The most famous MIR problem is probably music generation, or when a computer composes music. Another one is audio classification, which can either mean this sound is a piano and this sound is a flute, this song is a pop song and this song is a classical song, or even this note being played right now is an A and this next one is a C. Audio transcription sits at the intersection between note classification and music generation. Transcription is particularly interesting because the score is being learned from audio with no prior knowledge of the song. There have been several different approaches to audio transcription. Sugita used convolutional neural networks and a constant Q transforms representation. Kells broke each note down into the attack, decay, sustain, and release, and trained to recognize each. Then there was the output of a tuple with the start, end, note, and volume. Wang worked backwards and attempted to learn audio from the score using an encoder-decoder method taken from two autoencoders. And Hawthorne predicted the onset of notes and used that to predict what notes occur in a single frame. Unlike Sugita, I am using a recurrent neural network instead of a convolutional neural network. Unlike Kells, I do not care about sustain and release as separate entities from the notes. Unlike Wang, I'm converting from audio to score, and my encoder and decoder were not trained separately as autoencoders first. Unlike Hawthorne, I'm not using an onset predictor, and instead only care about if a note is present in a frame. My approach to audio transcription uses a recurrent neural network and a MIDI time series to learn what notes are being played each 64 milliseconds of a song. In a subsequent paper, Hawthorne also provided the Maestro dataset, which is what I am using for this project. The Maestro dataset is a set of 1,282 songs with both audio and MIDI counterparts, synchronized to be within 3 milliseconds of accuracy. The songs were all recorded using a Yamaha disc clavier piano. With over 200 hours of data and songs ranging from 45 seconds to 43 minutes, this dataset is incredibly useful for MIR projects and has been used in several different areas. If you're anything like me, you probably don't know what a Yamaha disc clavier piano is. This is a piano that records all of the MIDI information as it is played. Specifically, it records which note is pressed, how hard it was pressed, when it was released, and it records all of the same information about the piano's pedals. Here's a video of a Yamaha disc clavier piano being played in the 2008 International Piano E competition. Even though the piano has electronics in it, it's still a typical grand piano, which you can hear from the sound quality. In order to use the songs from the Maestro dataset, I needed to manipulate them to fit within my needs. All of the files should have the same format, and a WAV format is what worked with the libraries that I was using. If the file was already in a WAV format, as most of the files in the Maestro dataset were, the first step of reformatting was unnecessary. WAV files are typically in 44.1 kilohertz, but that means that there are 44,100 samples each second. This is quite a bit for a neural network of our capacity. 16 kilohertz is much simpler to work with. This means that there are only 16,000 samples each second, which is much smaller, but can still capture each note that a piano can produce. The songs ranged from 45 seconds to almost 45 minutes, so to ensure consistency and to only give small pieces to learn at once, each song was split into as many 10-second chunks as needed, with the last chunk being whatever was left until the end. The MIDI files, however, needed quite a bit more processing. Straight MIDI files are perfect for playing, but in order to be manipulated, the files should be easy to read for a neural network processing temporal sequences. To do this, the MIDI was initially converted into a MIDI CSV format. The MIDI CSV format gives the exact time in MIDI ticks that a given MIDI signal happens. What we care about is what note is on and what the velocity is at each new time point. The time series compiles each signal from the MIDI CSV format, and for every 64 milliseconds, marks if a note is currently on. This means that the notes clip to begin or end at exactly intervals of 64 milliseconds. So the representation does become less aligned, but only at a difference that is unlikely to be discernible to the average listener. Two different versions of these files are made, one with velocity and one without. Without velocity, the file ends up looking like a series of binary strings. And with velocity, the ones in those binary strings become values between 0 and 1. And again, the files were split into 10-second chunks for consistency's sake. This is what the MIDI file conversion process looks like. Initially, we have a MIDI file, often represented in this piano roll notation, where the y-axis shows the note to be played and the x-axis is the duration of the notes. If we zoom in here, you'll see that the time series representation of the MIDI file. This temporal format only marks changes that occur in the same 64 milliseconds and makes the changes happen all at the same time. Typical MIDI files aren't split into these time chunks, as each note is encoded at the exact time that it occurred. As you'll see, this representation only depicts the representation without velocity, where there are only ones and zeros. You might notice that the time series looks similar to the piano roll, just turned sideways, and that's basically what it is. The notes go along the top rather than the side, and the time goes down rather than across. Moving forward, we have the architecture of the neural network. The audio goes into a bidirectional LSTM layer and then feeds into a dense layer. This encodes the audio. The encoded audio is then fed into another bidirectional LSTM layer, and again this is fed into a dense layer before being decoded as the MIDI, and outputs the result as the binary CSV file representing the MIDI output. This is inspired by taking the encoding step of an audio encoder and the decoding step of the MIDI decoder and combining them to learn the MIDI from the audio. To train this network, I fed it one song, Variations Seriosus by Felix Mendelssohn from the 2013 Piano E competition. This song has 73 subsections, those 10-second chunks that I mentioned earlier, one of which sounds like this. This song is longer than both the average and mean songs in the dataset, at just over 12 minutes, which means we had a good amount of data coming from this one song. This one song training method is preliminary and was used to verify the architecture of the network and limit the amount of time spent training while doing so. It also serves as a proof of concept prior to training on multiple songs. After this training, I then tested the network by predicting with a completely different song, Sonata number 21, Opus 53, Waldstein, number 1, Allegro con brio by Ludwig van Beethoven from the 2017 competition, which you'll hear in a few minutes. The network was not trained on any part of this song, so currently I'm evaluating the results subjectively by listening to the real versus expected output. Once I show you the outputs, I'll explain why this objective evaluation approach is sufficient for now. These are the results from the neural network when it was not trained using any sort of velocity, that is, when the MIDI training examples were just ones and zeros. The waveform to the top left is the input, the audio representation, and the two piano rolls are MIDI representations, with the top being the output and the bottom the expected output. Here's what they sound like. First, the input that was given to the network. And next, the output created by the network. As you can hear, they definitely don't sound the same, but there are some similarities in the shape of the audio. Just to clear your head, this is what the MIDI file was supposed to sound like. So not only can you hear the differences, but visually the two MIDI files are obviously a little bit different. Specifically, you can see these lines here, and these lines, and then the general shape of the note spread. In the beginning of both of the MIDIs, all the notes are above the lines circled in blue, and after that, all the notes are below the lines circled in green. After that, the spread becomes a lot wider in both. You can also see, however, that the produced MIDI has notes both higher and lower than the original MIDI. Moving forward, we have the results from the neural network when it was trained with velocity. Again, the waveform to the top left is the input, and the two piano rolls are the given and expected output. Just to refresh, here's the audio again. And then the created output. Again, they don't sound the same, but they do sound abstractly similar. Finally, one more time, what the MIDI was supposed to sound like. Again, we can compare the MIDI files visually as well, and you may note that now they look far less similar. My current hypothesis, though, is that this is in part due to the fact that the visual representation does not account for any velocity, so several of the shown notes are very quiet. With more post-processing, we should be able to find what level is best to just count low velocities as 0. Looking again at those two lines in the true MIDI, you can see that the lower blue notes are still kind of there in the output, but really the green notes aren't. Again, though, you can see that a lot of the random notes are at the high and low end of the keyboard, but other than those, it is still relatively quiet below the blue and above the green. Once the true and expected outputs are more similar, we will begin using a more objective evaluation method, but so far these results are very encouraging. We're getting part of a lot of the notes. With more training, we should be able to get the full duration. Despite these current limitations, these are promising results and a good start towards directly transcribing music from audio with no prior knowledge of the score. After overcoming the initial shortcomings, and when we have more accurate results while training on one song, I plan to train the network on the entire Maestro dataset. To do this, the network will likely need to be deeper and will take more time and resources to train. Once the network is trained on more songs, I expect the accuracy of the output to increase to the point that pure auditory information will no longer be sufficient for true evaluation. At this point, I'll need to use an objective measurement to see the differences and similarities. I plan to compare the distance from the expected output for each note at each time segment, producing a mathematical evaluation metric. Although the main goal is still to produce a score that sounds like the original, which is the subjective goal, I want the output to be objectively as close as possible. Once the network works effectively on piano, I will attempt to train it on recordings with more instruments. This will lead to its own difficulties because there is no disc-cleaver piano equivalent for other instruments, but there still are MIDI versions of other instruments and songs from other instruments that are aligned. Once all of that works, we can use other audios that do not include instruments and see what the neural network thinks a train horn should sound like in terms of instruments. If you're interested in any of the papers that I discussed earlier, I have placed my references for you to look at. Thank you so much for listening to Deep Audio Transcription.